হ্যালো, শোনা যাচ্ছে? এম আই অডিবল? হ্যালো।
হ্যাঁ স্যার শোনা যাচ্ছে।
ওকে। Just 1 minute. So we are going to prove that if this version of prime evidence so we the set sigma is not proof, it is some hint type. S belongs to N such that there exists T belongs to R, T belongs to A, there exists an ideal J such that T plus J subset of union I equals to 1 to S, but but Tj not subset of Pi for each I belongs to 1 to S. So this is my uh, suppose the statement is not true, then sigma non-empty okay, because R is there. Choose a minimal element because it is natural number subset, so well ordering property it has minimal element, least element, this is called L sigma. Then there exists elements G, element G and ideal A such that G plus A subset of union Pi L, but G a generated ideal, that is G plus I. Not subset of Pi. For each I L, then check each step. I just write Pia intersection Pi is empty. If it is non-empty, then find a common element, then this condition will contradict. Check each step. Okay, check. Hence G plus subset of union I, since L is minimal element of sigma, we have subset of Pj for some J belongs to L and goes to I. We get subset of Pj, hence Pi Pj, because prime contradiction. As our claim has proved. Now G belongs to intersection of G belongs to intersection of Pi implies A is subset of Pi, and by previous version A subset of P J for some J or I, you can write L. This implies G subset of Pj for some J, again a contradiction. This implies sigma is empty, and we are done. So this is some sketch of this proof. You go through details. Okay. Prime avoidance is not true for infinite cases. Let field be a ring be a polynomial ring with indeterminate I don't write S. Then Pi equals to you write XIR, you can write it. This is I write R. Then Pi belongs to spec R and take I equals to ideal generated by Xi such that I belongs to natural number. Then I equals to union of Pi, but I don't not subset of Pi. So it is not true for is not true infinitely in phi case. That means infinitely many prime ideals. Lemma let is generated ideal Pi for prime ideals P1 to Pr. Then there exists B2 Bn to A such that C equals to monic in A1 answer is easy. Proof. Use this lemma. What is this? A plus I union, then Fi belongs to Pi. Contrapositively, if Fi does not belongs to Pi, then A plus I does not belongs to this. A plus I does not belongs to this. That means there exists an element A plus elements of I does not belongs to Pi. Then the one line proof. Set F equals to A1 and I equals to A2 to AN. So there exists then plus I does not subset of union Pi R. So there exists B2 to A that A plus summation AI Bi. F means AI. What is F? F equals to A1 sorry 2 to N does not belongs to so this is proved. And another lemma is let I1 be ideals in A and P belongs to spec A such that intersection I equals to 1 to M P, then of P sum so what is the case কিভাবে হবে এটা one line proof বলো একটু বলতে পারছি না intersection belongs to P, that means product is subset of P. P is prime. Now what can you say? What can you say? Think for 1 minute.
স্যার প্রোডাক্টটা থাকলে তো আই যেগুলোও থাকবে ও পি এর মধ্যে বাই প্রাইম অ্যাভারেন্স।
Prime avoidance.
হ্যাঁ মানে প্রোডাক্টটা থাকতে প্রোডাক্টটা ইন্টারসেকশনের সাবসেট, এবার সেটা ইমপ্লাই করবে তো প্রত্যেকটা আই যে পি এর মধ্যেই থাকবে।
প্রত্যেকটা
হ্যাঁ
প্রত্যেকটা থাকবে মানে ব্যাপারটা বুঝলাম না।
মানে ফর সাম, সরি প্রত্যেকটা থাকবে না, ফর সাম আর এর জন্য থাকবে।
Why?
প্রোডাক্টটা তো ইন্টারসেকশনের সাবসেট হবে।
Okay, I am writing this.
Sir, can we look like take contrapositive statement?
Hmm? You can. Now P is prime. What is the definition of prime ideal? You can proceed by contrapositive statement. That is okay. Now P is prime. Then अरे बोलो. I think I write R. Okay. But he is saying that contrapositive statement. If I R not subset of P for all R belongs to 1 to M, then there exists XR belongs to IR such that XR does not belongs to P. This is simply product XR R equals to 1 to N. This belongs to product II M and subset of P but none of XR. P contradiction since P is the prime. Same. Okay. Same statement. Now I am going to another page like 6. Definition. Let A be wavering homomorphism I subset of A ideal, J subset of B. That is not definition, I just write. Okay. F inverse J, what is this set? X belongs to A, so it is Fx belongs to J. Okay, I denote it by is an ideal of A. Check. This is called contraction J with respect to F. Notation J contraction. So J contraction is actually F inverse J. Okay, it is an ideal. It is ideal of A. If I need not be an ideal of B. Example, inclusion map Z to Q, 2Z goes to 2Z, 2Z ideal, I of 2Z. It is inclusion, to it is same as, but 2Z is not ideal in Q because Q is a field. Ideals are both 0 and Q. By proper, there is only proper ideal 0 is not in Q, as 2 belongs to 2Z, half belongs to Q, half into 2 does not belongs to 2Z. Okay, so this is not ideal, but if I B, what is this? Summation F X F A B, I write F A B A B. These are finite sum. Finite sum. So that A belongs to I and B belongs to B. Is an ideal of B. Check. This ideal is called extension of I with respect to F. Moreover, if F is surjective, then Fi equals to Fi B. Hence, Fi is an ideal. If F is surjective, then Fi is an ideal of J. Because Fib is ideal of Fi is an ideal of B. Notation I extension E, that is denoted by Fi B. All possible finite sum of this type Fa dot B. Okay. Now just see if x belongs to fi, then x is f a for some a belongs to I, x equals to fa into 1 that belongs to f I b. Okay, suppose summation fa b, I write I equals to 1 to n, this finite sum belongs to fi b, where ai belongs to I, bi belongs to b, 1 less or equals to for all I less or equals to n. Let bi equals to f si for all I 1 to n, since f is surjective. I should write here if suppose f is surjective. F is surjective. I should write here. Now, so one can write it as if ai bi I equals to 1 to n equals to summation f ai f si I equals to 1 to n equals to summation f ai si equals to 1 to n that belongs to fi. I can write it as equals to f summation ai si 1 to n that belongs to fi, because ai belongs to I for all I belongs to 1 to n implies summation finite sum ai si I equals to 1 to n belongs to I. So you see that if f is surjective, then they are same. So here you can say f I is subset of f I b, and here you can say that f I b is subset of f I. So from star and double star, we can say that f I equals to f I b. Okay. So next observation is contraction let P belongs to spec B, then F inverse P belongs to spec A. That is, contraction of a prime ideal is a prime ideal. It is very easy to prove it. Let AB belongs to F inverse P, if AB belongs to P, if B belongs to P, since P is prime, if Hence it is an ideal because contraction of an ideal is ideal. Here check, here it is your check. Now here is primality, so f inverse p belongs to spec A. Thus we have a map, therefore if A to B a ring homomorphism induces a map F star spec B to spec A, P goes to P contraction F inverse P. Okay, so ring homomorphism induces a now extension of a prime ideal may not be prime ideal. Give an example. Extension of a prime ideal may not be a prime ideal. Give an example. At example though. দিতে পারছো না? কি আশ্চর্য। Let consider Z x quotient x square. This is inclusion map. What is Z x quotient x square? Z x quotient x square is A plus bx such that belongs to Z. And you know what is your multiplication? A plus bx c plus dx is what is this? AC plus AC plus BD plus AD x, but x square is 0, so we'll remove this class. Okay, this class you can write plus x square.
So that is
Okay.
BC plus F.
Whatever you just
Okay.
multiply linearly, and if a coefficient of x square will vanish because it is coset. Now zero ideal is prime here, but zero extension is also 0 here, which is not prime because it is not integral domain. Okay, x dot x is 0, but zero extension, that is also 0. As it is not integral domain. Example, so one example is that let A, what is the example, what characterization of ideals of A mod I? A be a ring I subset of A be an ideal, then we have uh, canonical surjection by this is ring homomorphism also. So this is surjective, therefore if J subset of A is an ideal, then pi j is also an ideal. Okay, so note that if I write Q B and this is not this Q, if J an ideal of A mod I at first, then 0 plus I belongs to J. Every ideal contains 0. This is pi inverse plus I subset of pi inverse J. I put it as Q. Okay. Pi inverse J is ideal in A. Now what happened? Now what is 0? Inverse preimage of with kernel pi is I, because this is definition of coset. X plus I equals to 0 plus I if and only if x belongs to I. Okay, so this implies I subset of Q. Number 1, if now J equals to pi of pi inverse J, because pi is surjective. Now what is pi inverse J? Q. What is pi Q? That is Q mod J. What is pi Q? I just write one line here. What is pi Q? X plus I such that x belongs to Q. That is in my notation Q mod J. Conversely, if I subset of Q ideal, then pi Q is an ideal of A mod I, since pi is surjective. Hence, so what if J is ideal, then it look like Q mod J, where J is subset of Q. Sorry, I is subset of Q. And conversely, if I is subset of Q, then Q mod I is an ideal. Hence, ideals of A mod I are of the form Q mod I such that I is subset of Q deals. Okay, show that spec A mod I is P mod I such that I subset of P belongs to spec A, and max spec A mod I such that I subset of M belongs to max spec A. Okay, next some, okay, I go to another page, algebra. Properties sum. Just 1 minute. Or observation I write. Then I is I contraction extension. Number 2 J, sorry, there is no meaning of I contraction, sorry, I from here, so at first extend then contract. J is here, contract then extend. I extension is equals to extension contraction extension. J contraction equals to contraction extension contraction. Okay, proof. Just 1 minute. Let x belongs to I. This implies fx belongs to fi, that subset of fi b, because we have seen it here. Here fi is subset of fi b. Here is no use of surjectiveness of f. Second part you have to use that subjectiveness of f. Okay, this imply, what is this? I extension. This imply x belongs to f inverse I extension, that is equals to I extension contraction. So I is subset of I extension contraction. Number 2, let x belongs to J contraction extension, then x belongs to what? J contraction, then B, I should write F. Okay, x belongs to what? uh, b. So x can be written as f ai bi. Ai belongs to j contraction. This implies for all I, this implies f ai, what is this? J contraction means f inverse j, right? That is equals to f ai belongs to j. So this implies summation ai bi belongs to j. That means x belongs to j. So it is clear that I is if subset of if I is subset of I extension contraction, this implies fi is subset of fi extension contraction, this implies fib subset of extension contraction b. That means I extension is subset of I extension contraction extension. Now let y belongs to I extension contraction extension, that is fi extension contraction b. Y can be written as summation f ai bi, where ai belongs to f ai belongs to I extension contraction, I extension contraction. That means f inverse I extension for all I belongs to 1 to n. That means fai belongs to I extension. This implies summation fai bi belongs to I extension. Y belongs to I extension. Therefore, I extension contraction extension is subset of I extension. So from 1 or star double star we get four is similar homework. Next we define it is called Jacobson ideal of A, intersection of all maximal ideal. All since each prime ideal is a maximal ideal, sorry, each maximal ideal is a prime ideal, this imply intersection বেশি জিনিসের ইন্টারসেকশন নিলে কি হবে, ছোট হয়ে যাবে। if you get more sets then intersection will be smaller. This imply what is this, nil radical of Jacobson radical of A. Okay, nil radical is subset of Jacobson radical. Next, see that observation x belongs to Jack if and only if 1 minus xy is unit for all y belongs to A. Proof. Suppose x belongs to Jack A, x belongs to max spec. This imply 1 minus xy does not belongs to M if for all y belongs to A. 1 minus xy belongs to M and for all M belongs to max spec and for all if for some y belongs to A and some M belongs to max spec A, then 1 minus xy plus xy belongs to M, since x belongs to M so xy also belongs to M. This implies 1 belongs to M. Contradiction because it is a maximal ideal. So this implies 1 minus xy belongs to A minus union of M for all y belongs to A. 1 and this is a set of unit. Okay, A minus x, I write the 10 but A equals to set of units of A. 1 minus xy is unit of A, unit of A for all y belongs to A. Conversely, if 1 minus xy is unit for all y belongs to A, I claim that x belongs to intersection of all maximal ideals. If not, then what? If x does not belongs to M, some then what happened? M plus x equals to a, 1 belongs to this number, 1 equals to s plus xt. I write xy. So 1 minus xy s and given that 1 minus xy is unit, contradiction because unit lies in maximal ideal, therefore we have m belongs sorry x belongs to m for all this imply belongs to intersection okay. Recall that for any I, root I is x to the power n, x belongs to I such that x to the power n belongs to x belongs to a such that x to the power n belongs to I for some n greater than equals to 1. Now I subset of j root I subset of root j. Number 2, root I to the power n equals to root I. Number 3, root p equals to p. These are some observation, proof are easy. X belongs to root 1 root I, x to the power n belongs to I subset of j for some root j. Number 2, x belongs I to the power n I, this imply root I, let x belongs to root I, x to the power k belongs to for some k belongs to I, x to the power k n belongs to I to the power n, k belongs to I, k greater than 1, natural number. I should write natural number, that is better. What do you mean by greater or equals to 1? Where is the relation? This is better. should write n belongs to natural number. Okay, so this implies x belongs to root I to the power n. So root I is subset of root I to the power n. Hence let see that by definition take if n equals to 1, I is subset of root I. Okay, ideal. This is ideal. Okay, now it is obvious that by definition root p is subset of root p. Let x belongs to root p. This implies x to the power n belongs to p. This implies x belongs to p for some number, since p is the prime ideal. X to the power n belongs to p implies x belongs to p. So this implies root p also subset of p. Hence, if you have any question, please ask me. Otherwise, I will stop here for today. কোনো প্রশ্ন থাকলে জিজ্ঞেস করো। Okay, these are very basic and very easy content. In the ring category, you have ring homomorphism and rings. Now morphisms are ring homomorphism. Now ideals are very important in the ring category. So I studied today that under ring homomorphism, what is the characteristics of ideal. Okay, কি কি হয় এগুলো একটু স্টাডি করুন। ইফ ইউ হ্যাভ এনি কোশ্চেন প্লিজ আস্ক মি। কোনো প্রশ্ন থাকলে জিজ্ঞেস করো। Otherwise I will stop here. Okay.